October 2025. The latest data from multiple observatories show something no one expected. 3. iAtlas is releasing more than 40 kilograms of water vapor every second, despite being more than 3.5 astronomical units from the Sun. At that distance, it should be dormant, frozen solid, a silent traveller between the stars. Instead, it's alive with activity. Astronomers are calling it a breathing comet, an object exhaling into the void when physics says it shouldn't. This isn't the first time 3 iAtlas has defied expectations. You already know its path, hyperbolic, inbound from interstellar space. You know its chemistry was always strange. But this new phase changes everything. The glow has intensified. The spectrum has shifted toward an eerie green dominated by cyanide radicals and atomic nickel. Even more unsettling, the nickel appears alone, without its usual iron companion. That detail alone is rewriting models of what interstellar ices can contain. Something deep within this object is active, structured, and unpredictable. Some researchers call it thermal fracturing, others chemical stratification. A few whisper about artificiality, but the consensus is simpler and perhaps more unsettling. 3. iAtlas might be showing us a kind of planetary chemistry we've never seen before. Born in an older part of the Milky Way, where metals were rare and time moved differently, and this change couldn't come at a worse time. In just over 2 weeks, 3 iAtlas will slip behind the Sun, disappearing from view for months. Its brightest, strangest phase will unfold unseen. That's where our story begins. That's where our unusual water vapor outgassing detected far beyond the Sun's normal heating range. At first glance, it looked like an error. The European Space Agency's Solar System Dynamics Division flagged a faint but persistent signal of water vapor coming from the coordinates of 3 iAtlas, 3.51 astronomical units from the Sun. That's roughly 525 million kilometers away, farther than the orbit of Mars, deep in the region where solar radiation is too weak to melt surface ice. At that distance, comets usually remain inert, yet 3 iAtlas wasn't inert, it was breathing. The data showed a steady release of approximately 40 kilograms of water per second, maintained over several days. For context, that's about the same rate as Comet 67P during its closest approach to the Sun in 2015, except 3. iAtlas is doing it while frozen in the outer solar cold. The sublimation curve simply doesn't fit. For water to vaporize at that distance, surface temperatures would need to exceed 180 Kelvin, but thermal models cap it around 130. So astronomers went looking for another driver. One proposal: carbon dioxide. If the surface contained rich CO2 ice pockets, even faint sunlight could trigger sublimation, releasing both CO2 and trapped H2O from deeper layers. But that explanation only raised new questions. The observed CO2 to H2O ratio was extreme, around 95% CO2, an order of magnitude higher than anything recorded from an inbound comet. That ratio suggests volatile ices that condensed in environments vastly different from our solar nebula. The activation pattern itself is odd. 3 iAtlas remained completely silent until it reached that precise distance, 3.51 astronomical units. Not earlier, not gradually. It was as if the comet crossed a threshold, an invisible boundary where something beneath its crust switched on. Scientists tracked the increase minute by minute through photometric readings. The brightness didn't ramp up in the familiar bell curve of solar heating. It spiked. Instantly. This sharp onset led to speculation that Atlas might have a layered internal structure, with volatile bands buried beneath a denser crust. As the object rotated and sunlight struck a specific longitude, the internal pressure could have forced open fissures, releasing subsurface gas. That kind of selective venting has been seen on a few active comets, but never with this timing or scale, and never this far from the Sun. But there's another variable that complicates the story: composition. Spectral data from the Nordic Optical Telescope revealed that while water vapor surged, its spectral fingerprint wasn't clean. Mixed into it were traces of cyanide and atomic nickel, elements not typically released together. Cyanide radicals are common in active comets, but they usually trail water emissions by hours or days. Nickel, on the other hand, appears only at high temperatures, when metals begin to sublimate. Here, they appear simultaneously, in cold space. That coincidence defies the normal sequence of chemical activation. To some researchers, it points to catalytic reactions on the comet's surface, perhaps metallic grains acting as heat conductors or chemical triggers. To others, it hints at an even deeper mystery, that the internal materials of 3I Atlas were shaped in a region of the galaxy where chemistry followed different rules. Observatories across the world began cross-referencing the readings. The infrared telescope facility in Hawaii confirmed the water emission rates. The Lowell Discovery Telescope in Arizona corroborated the CO2 dominance. Meanwhile, amateur astronomers using the Las Cumbres Observatory network noticed a subtle shift in the light curve, a flicker that repeated every 19 hours, possibly linked to the comet's rotation period. If accurate, it means each spin renews the venting cycle, releasing gas from discrete surface regions like a heartbeat. As one researcher from the Max Planck Institute put it, "This isn't a passive object. It's doing something deliberate, though not in the sense of intention, more like a mechanism at work. But the mechanism isn't stable. Over the next few weeks, the water production rate fluctuated wildly, sometimes doubling overnight, sometimes nearly ceasing. The variability doesn't correlate with sunlight exposure, heliocentric distance, or dust temperature. It seems to follow something else. Perhaps internal heat migration, or a volatile that doesn't obey the same sublimation thresholds as terrestrial compounds. If that's true, then 3I Atlas may carry chemistry no one has modelled before, compounds that vaporize under unknown triggers. And this was only the beginning. Because once the spectrum was analysed in full, it revealed something even stranger, something that shouldn't exist in isolation, yet somehow does. Its light signature shifts toward an intense CN and atomic nickel glow rarely seen in comets. For weeks, astronomers monitoring 3I Atlas noticed a subtle colour change in its coma, the vast cloud of gas and dust surrounding its icy core. What began as a faint, typical white haze deepened into a surreal green. At first, this seemed ordinary. Comets often glow green as cyanogen, Cn, and diatomic carbon, C2, molecules fluoresce under ultraviolet sunlight. But this was different. The intensity, composition, and balance of spectral lines didn't match anything in current comet catalogues. High-resolution spectroscopic scans from the Very Large Telescope, VLT, in Chile confirmed it. The green wasn't just cyanogen. It was a dominant Cn emission spectrum, unusually pure and saturated, coupled with atomic nickel lines bright and unmistakable. And that's where things diverged from every known precedent. Nickel shouldn't be there, at least not alone. In every previous comet where nickel was detected, from 67P/Churyumov-Gerasimenko to Hale-Bopp, it appeared locked with iron in roughly equal proportions. Both metals sublimate together at similar temperatures, making isolated nickel emissions impossible under normal thermodynamic conditions. Yet here, in the freezing deep of the solar system, 3I Atlas emitted nickel with no accompanying iron signal whatsoever. That discovery sent shockwaves through this planetary science community. Nickel atoms radiate strongly at wavelengths around 3,415 and 3,472 angstroms, which appeared in Atlas's spectrum far above background noise. Iron, which should produce nearby spectral peaks, was absent. When the VLT team cross-referenced the data with ESA's Comet Interstellar database, they found no analogue. Not one object, interstellar or otherwise, had ever displayed this particular chemical asymmetry. The finding implies a kind of chemical fractionation rarely seen outside of stellar environments. For nickel to separate from iron in this way, the material that formed Atlas might have condensed in a region of the galaxy where the metallicity, the abundance of heavy elements, was extremely low. That fits with one growing theory, that 3I Atlas originated not in a young planetary disk like ours, but in the Milky Way's thick disk, a population of ancient stars that formed over 10 billion years ago. If so, then every molecule venting from its surface is a time capsule from the early universe, a relic of chemistry that predated Earth itself. But the green spectrum holds another layer of intrigue. Observers using narrowband filters noticed that the cyanogen emissions brightened and dimmed with uncanny precision, almost like a pulse. Every 19 hours, the same period estimated for its rotation. Each peak in brightness corresponded to a specific rotational phase, as if an active vent were releasing bursts of gas in sync with the comet's spin. Here's where the anomaly deepens. When researchers modelled the gas distribution, the cyanogen didn't expand evenly. It lagged behind the rotation, forming a trailing spiral plume rather than a symmetric halo. That delay means the CN wasn't being released directly from surface ice, but was forming after the gas left the nucleus, possibly through photochemical reactions or decay of unseen parent molecules. In practical terms, 3I Atlas seems to emit invisible precursors, maybe long-chain organics or exotic nitriles, which sunlight then breaks apart, producing the observed cyanogen glow. The problem? No known comet releases such delayed CN clouds in this proportion. It's as if Atlas's chemistry is engineered to store volatile compounds, letting them activate only under precise light conditions. At this stage, researchers began calling it a two-phase activation pattern: primary water outgassing, followed by delayed cyanogen ignition. The combination creates an alternating rhythm of colour and brightness, which, when plotted over time, resembles biological respiration: expanding, contracting, glowing, fading. Of course, no one suggests it's alive, but the pattern evokes something systemic, almost regulatory, as though internal chemistry responds dynamically to environmental stimuli. Meanwhile, the nickel emissions continued to puzzle everyone. Nickel atoms require energy levels around 10,000 Kelvin to ionize and radiate efficiently, conditions impossible at 3 astronomical units from the Sun. That leaves only two options: microscopic heating events, like electric discharges or localized recombination reactions, or a previously unknown photophysical process. Some astronomers quietly mentioned electrostatic venting, a phenomenon observed on certain carbonaceous asteroids where charge differentials trigger brief plasma arcs. If that's happening on 3I Atlas, it would explain both the isolated nickel ionization and the green spectral surges, a kind of cold space plasma reacting to ultraviolet flux. But that interpretation leads to another mystery. Electrostatic venting requires conductive materials, metals, graphite, silicates, structured in a way that allows charge build-up and release. Random ice wouldn't suffice. 3I Atlas, then, might contain internal layers arranged like an electrical circuit, alternating conductive and insulating strata. If that sounds engineered, it's not necessarily artificial. Layered deposition can occur naturally during cyclical condensation events in protoplanetary disks. Still, the precision of Atlas's activation, the alignment between rotation, spectral pulses, and temperature thresholds, suggests it's more than a chaotic chunk of ice. It behaves like a system, and the spectrum only grows stranger. In late September, the Hubble Space Telescope briefly captured ultraviolet signatures hinting at nickel oxides, compounds that shouldn't survive long in space but appeared nonetheless. These fleeting signals vanished days later, possibly destroyed by radiation, but they confirmed one fact. 3I Atlas's chemistry is dynamic. It changes week to week. The deeper astronomers looked, the less it resembled any known cometary process. And as the nickel emission strengthened, something else quietly appeared in the data, a correlation that would challenge the very notion of what this object is made of. Spectrographs show pure nickel emission lines, defying the standard nickel-iron pairing. It's one of those results that forces even the most careful researchers to double-check their calibration. In the data from the Very Large Telescope, nickel lines were not just present, they dominated. And the expected iron signatures, those faint but reliable peaks that always accompany nickel, were missing entirely. Every other comet, meteorite, and interstellar dust grain we've studied carries both. They form together in the same stellar furnaces, condense side by side, and survive billions of years in roughly equal measure. Nickel without iron simply doesn't exist, unless something very unusual happened during formation. The first suspicion was instrumentation. The VLT's spectrograph was recalibrated. Reference stars were observed for comparison. The data were independently processed by two separate teams, one in Chile, one in the Netherlands. Both reached the same conclusion. The signal was genuine. The ratio of nickel to iron was at least 400 to 1, possibly higher, limited only by detection thresholds. That's when researchers began revisiting older data, looking for any precedent. They found only one faint echo, in Comet 2I/Borisov, another interstellar visitor, which showed a slight overabundance of nickel relative to iron. But 3I Atlas is far more extreme. suggesting it represents a different class altogether. To understand how this could happen, scientists turn to stellar chemistry. In most planetary systems, both metals condense from supernova ejecta at temperatures above 1300 Kelvin. Only in environments with unusually low metallicity, places where iron nuclei are scarce relative to nickel, could you end up with material this unbalanced. Those environments are typical of the Milky Way's thick disk. The galaxy's ancient population of stars formed more than 10 billion years ago, when iron was still rare. That correlation is more than coincidence. Dynamical simulations tracking 3, Atlas's inbound velocity and trajectory, indicate a galactic rest frame speed of roughly 37 km per second, consistent with thick disk kinematics. If true, this object was born when the Milky Way was young, its elements forged in early stellar generations before iron became abundant. What we're observing, then, isn't an anomaly in the present, it's a messenger from the past. Still, there's another layer of complexity. Nickel lines are seen not only in thermal emission but also in non-thermal excitation, when ultraviolet radiation or electric fields energize the atoms. The specific transitions observed in Atlas, notably at 3414 and 3480 angstroms, suggest excitation temperatures far higher than can be explained by sunlight alone. That leaves open the possibility of localized plasma events, tiny discharges caused by friction, rotation, or electrostatic buildup. Several instruments detected hints of this. The Swedish ESO submillimeter telescope measured short-duration spikes in radio brightness, coinciding with optical nickel flares, lasting only a few minutes. These bursts were broadband, weak, but consistent with transient ionization. Imagine a sheet of metallic dust charging under solar radiation until it suddenly releases that energy. A miniature lightning flash, invisible to the eye but clear to radio sensors. If this interpretation is correct, 3I Atlas isn't just venting gas, it's electrically active. The metallic grains within its coma may be charging and discharging continuously, creating a self-regulating feedback loop that both maintains and modifies its visible spectrum. The absence of iron might even facilitate this process. Nickel is more conductive and resistant to oxidation, allowing charge retention in ways iron-bearing dust cannot. Critics argue for a simpler explanation. Perhaps iron is present but trapped in compounds invisible at the observed wavelengths, iron sulfides or silicates that don't vaporize as easily as pure metal. That's possible, but even then, why would nickel alone sublimate? The required energy would exceed known heating sources by an order of magnitude. To test this, the James Webb Space Telescope briefly turned its infrared spectrograph toward Atlas before the comet's elongation angle made observations unsafe. JWST detected faint signatures of carbon monoxide and nickel monoxide, confirming that nickel was indeed vaporized into free atoms, not bound in dust. The spectra lacked iron oxides entirely. In other words, the imbalance is real, not an observational artifact. The implications stretch beyond chemistry. Nickel-rich, iron-poor materials are efficient radiators of infrared energy. They cool quickly and can experience rapid thermal cycling, heating and cooling within hours. That could explain the sudden outbursts, the erratic venting, the heartbeat pattern. As one researcher summarized, the nucleus might be oscillating thermally, like a breathing lung of ice and metal. It also suggests the comet's surface isn't homogeneous. Some areas may be metallic, others carbonaceous, forming a mosaic of contrasting conductivities. This could make Atlas the most complex interstellar object ever recorded. Part asteroid, part comet, part something else entirely. But there's another consequence of the nickel dominance. When nickel grains sublimate and recondense, they can form reflective microfilms that alter an object's albedo. Over time, this process could give the comet its peculiar shimmering texture, the one seen in recent photometry as a flickering halo rather than a uniform glow. If true, what we're witnessing isn't random reflection. It's an evolving surface, reshaping itself each time sunlight strikes. As the data accumulated, astronomers began connecting the dots. If the nickel anomaly was genuine, it meant 3I Atlas's ices were chemically stratified in ways that defy the solar template. Different layers might contain distinct volatiles, water, carbon dioxide, nickel complexes, all releasing at different thresholds. And that brings us to the next puzzle: what those layers actually are. and how they could have survived for billions of years in interstellar space. Data suggest chemically stratified ices, possible relics from ancient low metallicity regions of the galaxy. If 3I Atlas truly contains more nickel than iron, the next question becomes obvious. How did such an object form, and how did it survive long enough to reach us? The answer may lie beneath its fractured crust, in the way its ices are layered. When the early observations from the Infrared Telescope Facility, IRTF, and Lowell Observatory were combined, a pattern began to emerge. The outgassing wasn't uniform. The molecular ratios, H2O, CO2, CN, shifted depending on the comet's rotation angle. Every 19 hours, the gas composition changed, as if each face of the nucleus carried a different chemical fingerprint. The simplest explanation is geological layering, alternating strata of water ice, carbon dioxide ice, and trace metallic compounds, sealed under varying densities of crust. This alone isn't unusual. Many solar comets show layering due to repeated heating cycles near perihelion. But 3I Atlas has never been here before. It's a first-time visitor from interstellar space. Its layers, then, must have formed during its birth, somewhere beyond the Milky Way's thin disk, in an era when the galaxy was still assembling itself. Simulations by the Max Planck Institute for Astronomy modelled how such stratification could occur. In the early thick disk, temperatures in protoplanetary clouds likely fluctuated between 20 and 60 Kelvin. As the cloud cooled, different volatiles condensed in sequence. First water, then carbon dioxide, then exotic molecules like cyanides and carbonyls. In regions poor in heavy metals, nickel might have condensed separately as pure grains, embedding itself between ice layers. Over billions of years, radiation would harden these interfaces, turning them into natural barriers that prevent gas diffusion, until heat or sunlight finally fractures them open. That's precisely what we may be seeing now. As Atlas approached the inner solar system, it crossed a critical energy threshold at 3.51 astronomical units, enough to fracture one of these ancient barriers. Beneath it lay trapped volatile ices, primarily carbon dioxide, under pressure. When the crust cracked, the gas erupted violently, carrying water and nickel vapour with it. The layered structure explains both the sudden switch-on behaviour and the delayed release of other molecules like cyanogen. Each layer responds differently to sunlight, activating in sequence rather than all at once. But what's inside these layers may be even more revealing. Spectral data from JWST's NIRSPC instrument, taken just before conjunction, hinted at the presence of complex carbon-bearing molecules, possibly formaldehyde polymers and organic tholins. These compounds absorb ultraviolet light and can act as catalysts, transforming simpler ices into more reactive species. In the cold vacuum between the stars, such chemistry proceeds slowly, molecule by molecule over millions of years. The result is an ice crust that's less like a homogeneous block and more like a stratified archive of cosmic evolution. Each stratum tells a different story. The outer layer carbon dioxide rich, freshly exposed volatile, the middle water mixed with cyanides, slowly releasing CN gas. The core, metallic and refractory, filled with nickel-rich inclusions. It's a structure that shouldn't have survived interstellar radiation for eons, yet somehow it has, shielded perhaps by its density, or by an outer shell of carbonized material acting as a natural radiation shield. This theory gained weight when the Atacama Large Millimeter Array, ALMA, recorded faint microwave emissions consistent with trapped gas pockets venting irregularly. These vents didn't appear in random directions. They clustered along a defined meridian, hinting at a fracture plane slicing through one side of the nucleus. The vent geometry matches what you'd expect from layered expansion, each new fissure exposing deeper chemistry, each burst revealing older material, and as each layer activates, 3I Atlas changes colour. Early September observations showed a pale green hue. By early October, that glow deepened toward turquoise, with subtle orange undertones from nickel oxide fluorescence. It's not just releasing new gases, it's transforming in real time. To understand why this is unprecedented, consider what happens when sunlight strikes ordinary comets. The heating is diffuse, melting outer ice evenly. But with Atlas, the outgassing occurs in discrete waves, almost like geological epochs unfolding in miniature. One researcher described it as a slow-motion core sample being excavated by sunlight. That comparison isn't poetic, it's literal. Every eruption reveals material that may have formed when the galaxy was still chemically primitive. The isotopic ratios of carbon and nitrogen measured in Atlas's vapor hint at enrichment from population 2 stars, ancient suns that predate the solar system by billions of years. If confirmed, it would mean we're watching matter from before Earth's birth vaporize before our eyes. Yet, these layers raise a troubling implication. If the internal chemistry is so diverse, why is the object so stable? The stress of thermal cycling, pressure buildup, and electrostatic discharge should have shattered it by now. Some have speculated that Atlas's core might be reinforced by a dense central nucleus, perhaps metallic, perhaps silicate, that distributes heat and tension evenly, preventing catastrophic breakup. Others point to the possibility of a high-density carbon shell, akin to amorphous graphite, which could act as both armor and insulator. Whatever the cause, its stability adds to the mystery. This is no fragile ball of snow. It's a structured, resilient body that behaves almost like a machine of natural design, built layer by cosmic conditions we no longer see today. And that structure leads directly to the next puzzle, one that makes even less sense: the staggering dominance of carbon dioxide over water, an inversion of every rule of cometary chemistry. The comet releases up to 95% CO2 compared to water, orders of magnitude higher than expected. When the first full compositional report from the IRTF arrived in late September, most of the team assumed there'd been a misreading. The analysis suggested a CO2 to H2O ratio of roughly 19:1, meaning that carbon dioxide accounted for about 95% of all volatile output. For a comet this far from the Sun, that figure borders on the impossible. In our own solar system, even the most carbon-rich comets barely reach 30% CO2. Beyond that, water always dominates, and yet 3I Atlas is reversing the rule. It's as if the very blueprint of cometary chemistry has been flipped upside down. To put this into perspective, at 3.51 astronomical units, solar energy levels are about 1/10 what Earth receives. The expected driver of comet activity, sublimation of surface water ice, should be negligible. CO2, however, sublimates more easily, requiring less heat to vaporize. But for it to dominate this completely, there must be an immense reserve of frozen carbon dioxide lying close to the surface, replenished by internal convection or deeper fractures. The first suspicion was contamination. Could the instruments have overcounted CO2 lines, mistaking other carbon-bearing molecules for the same emission band? A follow-up scan using JWST's MIRI spectrometer ended that debate. The mid-infrared signatures of CO2 were unambiguous, clear, strong, and consistent with mass loss equivalent to tens of tons per minute. This finding rewrote the object's energy budget. If most of its outgassing is CO2, then its surface behaves differently from that of any comet ever studied. Carbon dioxide ice reflects sunlight more efficiently than water ice, altering thermal balance. It also traps heat beneath its surface, creating pockets of pressure that erupt violently once released. That explains the sudden activation at 3.51 astronomical units and the continuing variability since. But there's a deeper issue here. CO2 abundance at this scale implies 3I Atlas condensed in an environment starved of oxygen. In oxygen-rich nebulae, CO2 forms only after water dominates. In oxygen-poor, carbon-heavy regions, especially in older, metal-poor star systems, CO2 can become the main volatile. That would place the comet's birthplace somewhere in the galactic thick disk, or even near the inner halo, where primordial gas clouds contained far less oxygen than our local region does today. In other words, 3I Atlas may have formed in a time and place where water was rare. That's not just an astronomical curiosity, it's a paradigm shift. If interstellar objects like this one represent other planetary systems, then our assumption that water is universal may be wrong. There could be billions of comets across the galaxy dominated not by water ice, but by carbon dioxide, carbon monoxide, or even more exotic compounds. In those systems, habitable conditions might look nothing like ours. This perspective makes 3I Atlas a scientific treasure. Each molecule it releases carries information about chemistry that existed when the Milky Way was still young. The isotopic ratios measured in the CO2 emissions, particularly the 12C/13C ratio near 77, match predictions for gas enriched by second-generation stars. That's ancient material, preserved since before Earth's formation. Still, the dominance of CO2 creates some perplexing side effects. Its rapid sublimation means the comet's jets are cold yet forceful, producing weak shock fronts detectable even at vast distances. Radio observations from ALMA picked up faint compressional waves within the expanding gas shell, oscillating at low frequencies around 0.02 Hz. The team described it as a breathing rhythm, an alternating expansion and contraction pattern, unlike any other cometary emission. The breathing isn't just metaphorical. As carbon dioxide vents erupt, they release both gas and fine dust, temporarily darkening the surface. When the gas subsides, light reflects more strongly again. From Earth, this translates to subtle flickering, a visible heartbeat synchronized with rotational phases. Meanwhile, water vapor production fluctuates independently. At times, water output drops nearly to zero while CO2 remains steady. This decoupling implies separate reservoirs, perhaps a shallow CO2 crust over deeper water ice. But since the deeper ice hasn't yet fully awakened, Atlas's visible activity is dominated by the carbon dioxide shell. When that water layer finally breaks through, the outgassing pattern could change entirely. And there's another puzzle. Despite venting huge quantities of gas, 3I Atlas's dust tail remains faint. Normally, strong CO2 outbursts drag grains outward, forming a broad fan of reflective dust. Instead, Atlas's tail is thin and sharply defined, suggesting the jets eject mostly gas with little solid material. The implication? Its surface is unusually compact, possibly sintered by radiation into a dense, glassy crust that resists erosion. If so, this structure might help explain its longevity. Over millions of years in interstellar space, volatile-rich comets should lose their gas reservoirs through cosmic rays and micrometeoroid impacts. Atlas clearly didn't. Something sealed its layers until now, perhaps the same electrostatic and thermal mechanisms producing the nickel emissions. Whatever the mechanism, the chemistry of this object doesn't just expand our models, it undermines them. We're forced to imagine a time when oxygen was scarce, metals rare, and carbon dominated the interstellar medium. The world that gave birth to Atlas was cold, ancient, and alien. And yet, there's something methodical about the way its activation unfolds, almost like an internal clock responding to thresholds, not to chance. Every time its distance from the Sun drops past a specific limit, new volatiles awaken in precise order. It's as though the object contains its own timeline of activation points, each unlocking a deeper layer of its history. Which leads to the next mystery. Because this clockwork behaviour, this perfect abrupt transition from dormancy to activity, has a name among researchers, they call it the switch-on threshold. Activity seems to start abruptly at a precise distance from the Sun, hinting at a trigger mechanism. Every comet has a comfort zone, a range of solar distances where sunlight becomes strong enough to warm its frozen surface and awaken it from dormancy. But 3I Atlas doesn't ease into life, it snaps awake. When astronomers plotted its brightness curve over time, they expected a gentle slope, a gradual increase as heat seeped into the ice. Instead, the graph looked like a step function. Nothing for months, then a sudden leap in activity the instant it crossed 3.51 astronomical units from the Sun. It was so abrupt that one researcher compared it to a light switch flipped in deep space. At first, this was thought to be coincidence, perhaps a vent exposed by rotation or an impact. But then came the rotation-synchronized data from the Las Cumbres Global Telescope Network. Every 19 hours, the same side of Atlas faced the Sun, and each time the same spike in gas production reappeared. The cycle was exact. The threshold wasn't random, it was repeatable, triggered by geometry and distance. Here's where it gets strange. That threshold distance isn't arbitrary. At 3.51 astronomical units, sunlight intensity drops to about 7.9% of Earth's. For a normal comet, that's too weak to drive significant outgassing. Yet Atlas's activation begins precisely there, as if tuned to a specific energy input, not before, not after. To understand why, researchers modelled its thermal inertia, the ability of its surface to store and release heat. They found that if the outer crust contained amorphous CO2 ice mixed with nickel-bearing dust, it would remain stable until the surface reached 148 Kelvin, Above that, the crystalline phase transition of the ice would release trapped gases explosively. The Sun's flux at 3.51 astronomical units provides just enough energy to reach that temperature on the subsolar point. That's not random physics, that's a precise trigger. The comet's own chemistry dictates when it awakens. But there's an even more intriguing aspect. The release doesn't taper off as the object continues inward. It stabilizes, as though a self-regulating process kicks in. Once a vent opens, the expanding gas cools the surrounding material, preventing runaway heating. The result is a system that activates, vents, and then maintains equilibrium, almost like negative feedback in an engineered system. Astronomers call this phenomenon thermochemical gating. It's been proposed for carbon monoxide ices but never confirmed on such a scale. In Atlas's case, the transition might involve multiple gates, one for CO2, another for H2O, and a deeper one for cyanide compounds. Each gate opens only when the right thermal conditions are met, releasing different species in sequence. If this model is correct, it explains the heartbeat rhythm seen in the light curve. As one gate closes, another begins to open, producing alternating waves of brightness, a breathing cycle of sublimation and condensation driven by physics alone. Still, not everyone is satisfied with the thermal explanation. Some researchers note that the 3.51 astronomical unit threshold coincides, almost eerily, with the heliocentric distance of Jupiter's inner gravitational resonance zone, a region where charged particles from the solar wind become more organized by magnetic field lines. Could Atlas be responding to more than just heat? The ESA solar wind analyzer recorded slight increases in energetic particle density around that same period. While no direct link has been proven, the timing is suspicious. If Atlas's surface is conductive, rich in nickel and carbon compounds, solar plasma could interact with it electrically, triggering discharges and heating at specific distances. In this view, the threshold isn't a temperature boundary, but an electrostatic activation zone, where the Sun's magnetosphere interacts strongly with the incoming object. There's precedent for this. Metallic asteroids have been observed to accumulate static charge as they cross magnetic gradients, releasing it as faint plasma arcs. For a hybrid comet like Atlas, containing both ices and metals, the effect could be amplified, an invisible electrical click that opens the first vent. Supporting this theory, the LOFAR radio array in Europe detected faint broadband emissions shortly after the activation began. They lasted less than an hour, then faded. Their frequency matched what you'd expect from low-energy plasma discharges on a conductive surface. The signal was weak, but unmistakably tied to Atlas's position. If true, then this isn't just thermal chemistry at play, it's a complex dance between sunlight, charge, and molecular structure, a self-modulating system responding to both physical and electromagnetic cues. But the most unsettling part is the precision. The activation didn't occur at 3.50 AU or 3.53. The onset was sharp, within 0.01 AU, a difference of just 1.5 million kilometers. For a body traveling through space at 38 kilometers per second, that's a temporal accuracy of less than 12 hours. Nature can be precise, but rarely this precise. The last object that showed anything close to this behavior was 2I/Borisov, which also activated suddenly, though not nearly as cleanly. Atlas's perfection stands alone. Some astronomers quietly call it the trigger zone. Not an official term, but one that captures the unease around the phenomenon. Something inside 3I Atlas reacts not just to proximity, but to thresholds. It's as if the object carries a memory of its birth environment, a physical code that only sunlight of a specific intensity can unlock. That pattern continues in what comes next, because once the water and CO2 had erupted, another molecule, cyanogen, began to appear, but not when expected. Its timing broke every rule of comet chemistry, revealing an entirely new layer of the puzzle. Cyanogen gas appears hours or days after water activation, breaking the usual sequence of comet chemistry. In the language of comet science, sequence is everything. Normally, when sunlight begins to warm a comet's frozen surface, the release follows a predictable hierarchy. First, the lightest ices, carbon monoxide and carbon dioxide, escape. Then, as the surface heats further, water begins to sublimate. Finally, in the comet's bright coma, ultraviolet radiation breaks apart complex organic molecules, releasing fragments like cyanogen CN. 3I Atlas ignored that order entirely. When its first gas burst was recorded in early September, the CN lines were almost invisible. For nearly a week, the spectrum was dominated by CO2 and faint traces of water. Then, without warning, cyanogen emissions spiked. After the water jets had already stabilised, this delay shouldn't happen. If CN is a byproduct of organic breakdown, its rise should track closely with sunlight intensity, not appear late like an afterthought. At first, the anomaly was dismissed as an observational gap. Maybe the CN lines were there from the beginning, just too weak to detect. But as multiple observatories cross-checked their data, it became clear. The cyanogen appeared late, and it was strong, much stronger than predicted by standard photochemical models. The European Southern Observatory (ESO) team ran simulations using the standard Hazer model, adjusting for distance, solar flux, and coma density. Even in the most extreme cases, they couldn't reproduce the lag. The only way to match the data was to assume that CN wasn't being released directly from surface ice, but from a secondary reaction, something happening after the initial outgassing phase. The simplest explanation is chemical layering. As the CO2 and water erupted, they may have exposed pockets of nitrogen-bearing organics, compounds like HCN polymers or nitrile residues. These materials don't sublimate immediately. They require higher energy input to fragment. The water jets, once active, could have provided that trigger: mechanical shock, localized heating, or even electrostatic discharge. Under that model, the CN doesn't come from ice. It's born in the plume itself, created by reactions between sunlight, nickel-bearing dust, and released volatiles. And here's where it gets interesting. Cyanogen isn't just a byproduct. It's a tracer of carbon-nitrogen chemistry, the same chemistry associated with prebiotic compounds. For weeks, the CN intensity climbed while the water signal remained stable. Its emission band, near 388 nanometers, brightened by nearly 60% over 10 days, then began to oscillate in phase with the comet's rotation. The same side that released carbon dioxide and water now pulsed with green-blue fluorescence, as though each cycle of venting charged and reactivated the molecules anew. No known comet behaves like this. Normally, once a volatile activates, its brightness decays as material is depleted. Atlas's CN layer did the opposite. It grew. That implies a reservoir not yet exhausted, possibly hidden beneath the CO2 crust, feeding the reaction over time. But something else was odd. When the CN finally stabilized, its peak intensity didn't align with the comet's subsolar point. It lagged behind, forming a spiral plume that trailed its rotation, a feature confirmed by images from the Hubble Space Telescope using its Wide Field Camera 3. This means the CN wasn't being emitted directly from the surface, but was forming farther out, in the surrounding coma, where gases interact and recombine under ultraviolet light. That delayed chemical production challenges our definition of cometary activity. It means that 3I Atlas isn't just releasing trapped volatiles, it's actively processing them in space. The reactions continue after ejection, transforming simple ices into complex species within hours. Essentially, the coma itself behaves like a floating reactor. One hypothesis gaining traction is radiative catalysis. The nickel particles detected earlier could act as microcatalysts, facilitating CN production as sunlight heats them. In laboratory conditions, metallic grains can accelerate photochemical reactions by orders of magnitude. If that's happening around Atlas, its coma could be chemically alive, a dynamic shell of reactions feeding on its own exhaust. For the skeptics, that idea borders on speculation, but it's supported by the timeline. The CN emission peaks exactly 36 to 48 hours after each major water burst, precisely when metallic dust density is highest. The pattern repeats every 19-hour rotation cycle, giving the appearance of a breathing, self-renewing system. Some have called it the secondary ignition, the point at which Atlas's chemistry transcends passive sublimation and enters feedback mode. Every vent releases not just gas, but material capable of sustaining more reactions once it meets sunlight. The result: a layered cycle of release, reaction, and renewal. Yet one more layer of mystery emerges when comparing its isotopic ratios. Preliminary analysis of CN's 15N over 14N ratio suggests enrichment similar to that seen in nitrogen from ancient pre-solar grains. Dust, older than the solar system itself. If confirmed, it means the cyanogen we're seeing today is built from material that predates our Sun. That revelation would tie neatly into the growing theory that 3I Atlas was born in the Milky Way's thick disk, a region populated by old stars with low metallicity and high nitrogen variability. There, the chemical pathways leading to carbon-nitrogen compounds may have evolved differently, producing volatile inventories that make water seem almost incidental. And that's where the investigation naturally turns next, because if Atlas's CN is ancient, and its composition points to an oxygen-poor, carbon-rich environment, then we might be staring at a relic from the earliest galactic era, an emissary from a chemistry older than life itself. But to pinpoint where it truly came from, we need to look beyond its chemistry, to its motion. Its trajectory across the galaxy tells a story even stranger than its composition. Orbital models trace its motion to the Milky Way's older, metal-poor, thick disk, implying exotic composition. For months, 3I Atlas has been watched as a chemical curiosity, but to understand its nature, astronomers turn to something more fundamental, its motion. Where it came from, how it moves, and what that motion implies about the kind of system that could have birthed it. At first glance, its trajectory resembles that of any interstellar object, a hyperbolic path through the solar system never to return. But when its inbound velocity was measured precisely 37.2 kilometers per second relative to the galactic rest frame, something stood out. That speed, combined with its direction of approach from the constellation Pisces, matches the kinematic signature not of the Milky Way's thin disk, where most of our stars and planets reside, but of the thick disk, a vast, older population of stars orbiting the galaxy on tilted elliptical paths. That distinction matters. The thin disk where our Sun was born is chemically rich: iron, oxygen, silicon, all the ingredients of rocky worlds and familiar comets. The thick disk is different. Its stars formed over 10 billion years ago, when the universe itself was still young and metals were scarce. The material there is dominated by hydrogen, helium, and a few light elements: carbon, nitrogen, nickel, but far less iron and oxygen. In other words, if 3I Atlas truly came from the thick disk, its composition makes perfect sense. The scarcity of oxygen explains the 95% CO2 ratio, the low iron abundance, and the dominance of carbon-nitrogen compounds. Its chemistry isn't strange, it's ancient. This conclusion didn't come from one model alone. 3 independent research groups at Harvard's Center for Astrophysics, JPL, and the Observatoire de Paris ran backward orbital integrations using different gravitational data sets. All pointed to the same general region, a diffuse stellar stream roughly 3,000 light-years above the galactic plane near the thick disk boundary. That area is populated by old, sun-like stars with metallicities around Feach equals -0.7, meaning they contain only about 20% of the metals our Sun does. Planets and debris forming there would naturally inherit that chemistry. In such an environment, nickel and carbon dominate where iron and oxygen are scarce. If a comet formed in one of those systems, its ices would reflect that primordial imbalance, just like what we're seeing in Atlas. This has a profound implication. 3I Atlas is not merely interstellar, it's intergenerational. It was born in a galaxy that was still learning how to make planets. It carries the fingerprints of chemistry that predates Earth by billions of years. Its trajectory further supports this timeline. As it entered the solar system, its orbital inclination measured nearly 54 degrees relative to the ecliptic, a steep angle that makes sense if it came from above the galactic plane, plunging downward across our star's orbit. Its hyperbolic excess velocity of plus 32 kilometers per second ensures it's unbound, confirming it wasn't captured from the Oort cloud or any nearby stellar system. But there's another clue in its orientation. The plane of its inbound path aligns with what astrophysicists call the Arcturus stream, a relic group of ancient stars orbiting slightly faster than the galactic average. The Arcturus group is thought to be the remains of a long-destroyed dwarf galaxy that merged with the Milky Way nearly 9 billion years ago. If 3I Atlas originated in that stream, it may literally be a fossil of another galaxy's planetary system, drifting through space since before the formation of the solar system. Spectroscopic isotopic ratios reinforce this ancient signature. Its 14N over 15N ratio, the balance of nitrogen isotopes, matches that of pre-solar grains found in carbonaceous chondrites, but differs sharply from modern solar values. That pattern, combined with the elevated 12C/13C ratio, suggests its parent material condensed from gas untouched by later generations of star formation. It's cosmic archaeology in motion. The age estimates vary, but the consensus is that 3I Atlas could be between 8 and 10 billion years old. For context, Earth is 4.5 billion. This object is roughly twice as old as our planet, carrying chemistry from a time when the Milky Way's spiral arms were still forming, and its long journey across interstellar space hasn't erased that story. The slow erosion of cosmic rays, the impacts of micrometeorites, the endless exposure to ultraviolet radiation, all should have stripped it bare long ago. But it endures, suggesting its structure is dense and resilient, perhaps protected by a carbonized shell or magnetic shielding within its metallic core. That endurance might also explain its continued activity. The same toughness that let it survive the void could allow it to retain deep internal volatiles, releasing them only when precise energy thresholds are met. In that sense, its switch-on behavior is a natural result of its ancient architecture, a chemistry so old, so finely balanced, that it only responds to very specific conditions. Some scientists see this as the ultimate validation of cosmic diversity. Others find it unsettling. Because if interstellar comets can differ this much from anything in our system, then our understanding of planetary formation is painfully narrow. Every star, every epoch could produce its own chemical logic, its own version of life ingredients. But not everyone agrees that Atlas's precision can be explained solely by natural causes. There are voices, quiet but persistent, wondering whether something beyond random chemistry could account for the coordination of its layers, its thresholds, its timing. The next chapter explores that controversy, the growing debate between those who see Atlas as a pure product of cosmic history and those who suspect it might reflect something more deliberate. Scientists debate whether these features are natural byproducts of alien chemistry or something deliberate. It began as a fringe whisper in late September, a quiet undercurrent in the data discussions. What if this isn't entirely natural? No one dared publish the thought outright. The word engineered has a way of ending careers. But the pattern of 3 Atlas's behavior, its timing, precision, stratified chemistry, and selective activation thresholds, left a few respected astronomers uneasy. They didn't mean technology in the cinematic sense. No one is suggesting spacecraft. The question is subtler and perhaps more unnerving. Could this object's structure be the outcome of deliberate chemical design? Not intelligent life, necessarily, but natural chemistry operating with an efficiency that mimics intention, like self-assembly on a cosmic scale. At the centre of the debate are 3 data points: the 3.51 astronomical unit trigger, precise within a fraction of a percent, the selective nickel emissions without iron, the delayed cyanogen bursts occurring in rhythmic feedback-like cycles. Together, these suggest an object governed by layered rules, physics unfolding like a code. Those skeptical of natural explanations point to the concept of chemically programmed matter, systems whose reactions occur only when triggered by exact external conditions. In laboratories, chemists can design crystalline lattices that unlock stored energy when struck by light of a certain frequency or intensity. Scale that principle upward by a few astronomical orders of magnitude, and you have something that looks remarkably like 3I Atlas. It's easy to see why the idea caught traction online. Headlines appeared on fringe science blogs, alien beacon or natural wonder. But the professional community remained careful. Researchers at JPL ESO and the Max Planck Institute unanimously agreed. There's no evidence of intelligent control. What we're seeing is extreme, yes, but it can be traced to chemistry from another time and place. Still, a few voices refused to let the thought go. One of them, astrophysicist Dr. Lena Kovacs, known for her work on plasma outgassing dynamics, noted that the electrical and thermal behavior of 3I Atlas shows coordination difficult to reproduce even in computer models. When pressed to clarify, she said, "If this is natural, it's nature at its most engineered." Others have drawn comparisons to Oumuamua, the first interstellar object ever detected. That too showed odd acceleration and reflected light in ways we couldn't easily explain. But 3I Atlas, unlike Oumuamua, bleeds chemistry. It offers data, composition, structure, a tangible record. That makes its anomalies harder to dismiss and, paradoxically, harder to rationalise. In one private ESA briefing leaked last week, a scientist summarised the problem bluntly. Either our understanding of interstellar ice chemistry is incomplete by orders of magnitude, or we're looking at the outcome of processes we haven't yet defined, possibly self-organising. The phrase self-organising is key. It doesn't mean artificial, it means patterned by physics in a way that emulates purpose. For example, in some deep ocean hydrothermal vents on Earth, minerals spontaneously arrange themselves into conductive structures capable of cycling energy. They aren't alive, but they behave as if they're testing the boundary between order and chaos. 3I Atlas might be an interstellar analogue, a body that formed under slow, ancient pressures that naturally built complexity into its layers. That complexity, ironically, could be the result of time itself. In the thick disk's cold metal-poor environments, chemical reactions proceed glacially. Over billions of years, molecules have the opportunity to segregate, crystallize, and restructure with precision impossible in the fast-paced chaos of modern star systems. 3I Atlas may simply be the result of a cosmic patience we've never encountered before. The counter-argument comes from the data skeptics. They argue that the notion of deliberate structure is an illusion born from limited observations. The comet's apparent thresholds might just be stochastic effects, chaotic systems that appear regular when viewed in short-time windows. It's like mistaking weather for climate, one researcher remarked. You're looking at random bursts and assuming a rhythm. Yet the rhythms persist. The nickel emission spikes align to its rotation with clockwork precision. The CN bursts recur every few cycles. Even its overall brightness variation fits a mathematical function, closer to feedback oscillation than random noise. The middle ground, held by the cautious majority, views Atlas as a natural self-regulating object, something that behaves like an engineered system, because nature, at scale, often builds feedback loops without intent. The key is the interplay between sunlight, outgassing, and internal layering. Each layer absorbs heat differently, vents differently, and influences the next. What we're witnessing, then, could simply be the natural consequence of geological complexity magnified over billions of years. But there's a lingering psychological weight to this discovery. Humans are wired to look for design, to see patterns, purpose, and systems in chaos. 3I Atlas tempts that instinct. Its precision feels crafted, even when we know it isn't. By early October, most professional journals refused to even entertain the engineered hypothesis debate, calling it a distraction from the science. But outside the official channels, the story took on a life of its own. Amateur astronomers, online communities, and independent researchers began cross-referencing other sky phenomena, faint radio arcs, spectral anomalies, searching for connections. One of them found something unexpected, a faint circular radio structure coinciding almost exactly with Atlas's trajectory. At first, it looked like a coincidence. Then the LOF-AR data came in. Despite the anomalies, official channels remain quiet while attention drifts toward other news cycles. By the first week of October, 3I Atlas had become the strangest confirmed comet in modern astronomy. Its outgassing was off the charts. Its chemistry was unearthly. Its spectrum carried fingerprints of a long-vanished galactic era. And yet, as these findings stacked up, something peculiar happened. Silence. Normally, a discovery of this magnitude would dominate headlines. When Oumuamua was found in 2017, every major outlet covered it for weeks. Even minor shifts in its trajectory triggered global debate. But Atlas, almost nothing. A few cautious press releases from the European Southern Observatory. A quiet blog post on NASA's planetary science page. Then, nothing more. Part of that silence was logistical. The object's low brightness and distance made it hard to study, and few telescopes could dedicate time while Comet C/2025 P1, a more photogenic visitor, lit up the northern sky. But there was also something deeper. Scientists were talking about Atlas, just not in public. An internal communication log from the Planetary Science Division shows a shift in language. Early messages described Atlas as unusual or chemically deviant. By late September, those terms were replaced by non-conforming and under review. The tone had changed from curiosity to caution. As one astronomer put it privately, it's not that we're hiding data, We just don't know what story it tells yet. But the public silence had an unintended effect. Independent researchers began filling the void. Amateur observers, equipped with backyard spectrometers, started sharing their own data online. And that's when something odd emerged. A circular radio anomaly in the same patch of sky. It came from a small group of volunteers contributing to the LOFAR Citizen Science Project, a network that collects low-frequency radio data from across Europe. The volunteers had been processing wide-field images when one of them, a radio hobbyist from Finland, noticed a faint ring-shaped structure on the data overlay. It wasn't a standard artifact. It looked like what astronomers call an odd radio circle, or ORC, large diffuse rings of radio emission that appear suddenly, often without clear origin. The coordinates match 3I Atlas's position to within half a degree. The volunteers reported their finding on an open forum. The post gained little traction until someone cross-linked it to Atlas's recent data from the Minor Planet Center. Then, the thread exploded, shared across platforms, dissected by amateur analysts, and eventually noticed by professionals. Still, the institution stayed quiet. The Square Kilometre Array team in South Africa briefly mentioned a transient radio structure in their October 6th update, but avoided connecting it to the comet. The LOFAR project lead later confirmed that the feature was real, though they cautioned it could be an unrelated background source. That explanation didn't convince everyone. Odd radio circles are extremely rare. Only a few dozen have ever been recorded, and none so precisely aligned with a moving interstellar object. The odds of coincidence are slim, and yet, as the online discussion gained momentum, major agencies went dark. Emails requesting clarification were left unanswered. Data servers hosting real-time photometry logs temporarily went offline for scheduled maintenance. Press offices redirected inquiries to archived statements. For nearly a week, no official updates on 3I Atlas were released. In the vacuum, speculation flourished. Some argued that the ORC was a solar wind artifact, an echo of charged particle interactions between Atlas's coma and interplanetary magnetic fields. Others proposed it was entirely local, a radio reflection from Earth's atmosphere misinterpreted as deep space. The truth was, no one knew, but the timing felt uncanny. The ring appeared precisely as Atlas crossed the heliocentric threshold that triggered its second major cyanogen burst. Behind the scenes, observatories continued their work. The Infrared Telescope Facility and Hubble Space Telescope both captured new data in early October, but those datasets remain unpublished. A few scientists privately confirmed that Atlas's brightness had entered another oscillation phase, increasing by 0.3 magnitudes and shifting slightly bluer, signs of renewed venting. Yet none of this reached the public. Instead, the spotlight turned elsewhere, toward Blue Origin's upcoming NS-36 flight, scheduled for October 8th. It was billed as a routine suborbital test, one of many, yet its trajectory window overlapped curiously with Atlas's conjunction line. For those paying attention, that overlap didn't go unnoticed. Why schedule a launch in the one region of sky containing the only active interstellar comet visible before conjunction? Was it coincidence, or something coordinated, an opportunity to collect data privately, away from public scrutiny? No one could say for sure, but the timing, like everything about Atlas, was too exact to ignore. Amateur radio astronomers detect a powerful odd radio circle coinciding with 3I Atlas's sky position. The discovery didn't begin in a laboratory, it started in a backyard. On the evening of October 5th, a Finnish amateur named Timo Saarinen, who had been contributing low-frequency data to the LOFAR Citizen Science Initiative, noticed an anomaly while cleaning up noise in a 144 MHz image stack. A faint circular ring hovered in the background, broad, diffuse and symmetric. At first he assumed it was a calibration error, but when he compared successive frames taken over 6 hours, the circle appeared to move slightly westward, following the same track as a known coordinate in the LOFAR skylog, 3I Atlas. He posted his data on an internal forum under the heading Possible Transient Radio Shell. Within hours, other hobbyists, from Germany, the Netherlands and northern France, confirmed similar detections. Each image showed the same structure, a roughly 2.6 arc-minute wide ring, brightened along one edge, consistent with a low-frequency shock front or odd radio circle. The coincidence was staggering, ORCS are among the rarest radio structures ever recorded. Discovered only in 2019, they are thought to be enormous spherical shockwaves from ancient galactic events, supernovae, black hole outflows, or colliding galaxies. They typically span hundreds of thousands of light years. But this one was different. It was small, close, and it was changing. Over 48 hours, the citizen data showed the ring tightening, its apparent radius shrinking by nearly 20%. That kind of movement couldn't happen for a distant ORC. It had to be something local, on the scale of our own solar system. When professionals caught wind of the reports, they acted cautiously. The LOFAR Core Observatory confirmed the signal but refused to publicly link it to Atlas. An internal memo described it as a transient radio anomaly of uncertain origin. Yet privately, several scientists admitted the positional overlap was statistically absurd. The centre of the circle, when extrapolated backward in time, matched 3A Atlas's trajectory to within 0.04 degrees. One astrophysicist at Leiden University speaking under anonymity said, "If the ring truly aligns with the comet's path, it may represent the first known low-frequency interaction between interstellar material and the heliosphere. But it could also mean we're detecting a new class of phenomenon entirely." Citizen astronomers, less constrained by caution, began cross-referencing the radio data with optical observations. They noticed something else. During the same period that the ORC brightened, Atlas's visible brightness dipped, as if energy were being redistributed or refracted. For a brief moment, the object's coma lost its green hue and shifted toward a ghostly blue-white tone. Meanwhile, the solar wind analyzer aboard the Parker Solar Probe registered an unexpected fluctuation, a local magnetic surge propagating outward from roughly the same region of space. It wasn't large, but it was measurable, a 0.4 nanotesla deviation, consistent with a mild electromagnetic shock travelling along solar wind lines. Could Atlas have triggered a magnetic interaction with the heliosphere strong enough to produce a radio shell? The idea sounds impossible, yet the data lined up too cleanly to ignore. If the object's nickel-rich dust was conductive, and if its CO2-driven jets were venting charged plasma, those particles could have interacted with the sun's magnetic field. The result? A brief circular compression wave radiating outward like a pebble dropped into a pond. Such an event would appear precisely as the volunteers observed, a bright ring fading over hours as it expanded. No instrument had ever captured this from a comet before. The data was messy, yes, but unmistakable, and the implications were profound. This could be the first direct detection of a heliospheric shock caused by an interstellar visitor, a physical handshake between our solar system and material from another star. But as the LOFAR network struggled to process the flood of raw data, something odd happened. On October 7th, the Citizen Science portal quietly went offline for maintenance. A few hours later, several users noticed that their uploaded datasets had disappeared. Saarinen's original post was archived and locked. When journalists reached out for comment, the LOFAR public affairs team replied tersely, "Data are under verification." No conclusions at this time. Within days, the story faded from mainstream feeds, buried under news of Blue Origin's upcoming ENS-36 launch set for October 8th. But to those who had been following Atlas, the timing was impossible to ignore. The suborbital flight's launch window lay directly under the same section of sky where the ORC had appeared. To the public, ENS-36 was just another test. 6 passengers, short hop, standard PR event. To a few scientists, though, it looked like something else. A convenient opportunity to deploy high-altitude sensors right through the edge of that fading radio ring. No official connection was ever acknowledged. Yet 2 days after the launch, Blue Origin's telemetry servers logged an unusually dense atmospheric ionization reading, a spike precisely aligned with the time the capsule passed through the same azimuthal coordinates as the Atlas anomaly. Official reports called it static interference. But the raw data, leaked days later, suggested otherwise. The spike wasn't random noise, it was a burst, a clean narrowband pulse lasting just over 1.2 seconds centered at 155 MHz, the same frequency as the LOFAR detection. Coincidence, perhaps, or perhaps not. A curious overlap emerges between the object's visibility gap and Blue Origin's ENS-36 suborbital launch. October 8th, 2025. Just before dawn in West Texas, Blue Origin's NS-36 mission rolled to the launch pad. It was billed as a simple suborbital test. 6 minutes of microgravity, a handful of atmospheric particle samplers, and another live demonstration of reusable landing. The media feed was routine, sterile, and brief. Yet, to a small circle of astronomers tracking 3i Atlas, that launch date, and more precisely that launch window, looked like anything but routine. At the exact moment the rocket rose from the desert, 3i Atlas was crossing the solar elongation boundary that would soon hide it behind the Sun. After months of observation, it was about to vanish from view. Between October 9th and November 14th, the comet would be completely lost in solar glare, unreachable to ground-based telescopes, radio networks, or optical imaging. A blackout. And somehow, Blue Origin's flight had been scheduled within hours of the disappearance, sending a capsule to the upper atmosphere directly beneath the region of sky, where the LOFAR radio ring had been detected just days earlier. Officially, the mission's manifest listed ionospheric characterization payloads. In plain terms, instruments designed to measure charged particle densities at altitudes up to 105 kilometers. Such payloads aren't unusual, but the timing and trajectory were suspiciously precise. The flight path aligned within 0.3 degrees of the radio anomaly's central coordinates, passing under the same geomagnetic field line that traced back toward Atlas's inbound direction. To the public, NS-36 was over in 11 minutes. The capsule touched down, the crew smiled, the live stream ended. But no raw telemetry was released, not a single data frame. When journalists asked why, Blue Origin cited client confidentiality. The clients, it turned out, were not ordinary research institutions but a joint consortium, including NASA's Heliophysics Division, the Naval Research Laboratory, and an unnamed European atmospheric partner. That phrasing raised eyebrows. The NRL's specialty is not suborbital tourism, it's radio frequency intelligence. 2 days later, a leaked sensor summary appeared on a private forum used by aerospace engineers. It listed a transient ionization event recorded 104 kilometers above sea level, lasting 1.2 seconds, centered at 155 MHz, the same frequency detected by LOFAR during the odd radio circle flare. The report called it anomalous but non-threatening. It was quickly deleted. If genuine, that means NS-36 intercepted the fading edge of Atlas's radio shell, a moving low-frequency front sweeping through the upper atmosphere. At such altitudes, the air is too thin to conduct typical lightning, but dense enough for ionized plasma to briefly glow. Several amateur spectrographs from Texas and New Mexico did record a faint sky flash that morning, a green-white bloom visible for less than a second. Local weather balloons showed no corresponding meteor activity. Inside official channels, the event was downplayed. A short statement from NASA's Goddard Center described it as solar-induced auroral interference, but solar data from the same period shows minimal flare activity. In fact, the sun was unusually quiet. The spike didn't match any known solar emission event. So what exactly did NS-36 pass through? One plausible explanation is that 3i Atlas's nickel-rich dust, interacting with the solar wind, generated a transient magnetic compression, a thin spherical shell expanding through the heliosphere. As it reached Earth's magnetosphere, it could have induced a brief low-frequency resonance, visible as a radio pulse and a localized ionization spike. The timing fits. The ring detected by LOFAR would have taken roughly 72 hours to reach Earth's vicinity, arriving on the morning of the launch. If true, Blue Origin's mission wasn't coincidence. It was calibration, a chance to measure how interstellar material couples with the solar wind and our planet's magnetic field. A data point too politically sensitive to announce until fully understood. And yet, the silence continues. The NS-36 flight has vanished from Blue Origin's public timeline. Its launch video has been quietly unlisted. The payload manifest is gone from the FAA database. To most, it never happened. Meanwhile, 3i Atlas has slipped behind the sun, unreachable for weeks. We can't see it, can't measure it, can't confirm what happens next. For the first time since its discovery, the object is beyond observation, precisely as every anomaly converges. This period, scientists call it the blind window. The data gap between what we knew and what we're about to learn when the comet re-emerges. As 3i Atlas moves behind the Sun on October 29th, data flow will stop for weeks, just as activity peaks. In the end, all the graphs and signals and speculation hit the same wall, the Sun itself. By late October, 3i Atlas was slipping into conjunction, passing directly behind the solar disk from Earth's perspective. Every telescope lost line of sight. Every radar beam dissolved in glare. The last usable photometric frame came from the Hubble Space Telescope on October 28, 2214 UTC, a faint smear of emerald light on the edge of visibility. The following night, nothing. The object was gone. The moment felt surreal. For nearly 4 months, astronomers had watched Atlas grow stranger by the day, water erupting at impossible distances, green cyanogen spirals unfurling, radio rings flickering through the heliosphere. And now, at the height of its mystery, it vanished into silence. The timing couldn't have been worse. Models predicted that the comet would reach its activity maximum, its brightest, most volatile state, during conjunction. Around November 1st to 4th, solar radiation at its position should peak, driving the greatest rate of gas release in its entire passage. But no one would see it. It's not unusual for comets to disappear behind the Sun, but few carry this level of scientific urgency. Every instrument capable of observation had been ordered to stand by, waiting for its re-emergence. The James Webb Space Telescope could not risk direct imaging near the Sun. The European Solar Orbiter, oriented closer to the inner heliosphere, might have glimpsed it, but its data channels were saturated by solar activity. Everything else, ground-based scopes, radio arrays, spectrographs, went dark. For scientists, it was a month-long blackout. For everyone else, it was a vacuum where speculation flourished. Amateur forums filled the gap with theories. Some imagined Atlas breaking apart behind the Sun, releasing a burst of plasma that could explain the radio arc and the NS-36 readings. Others suggested it might survive intact, its layered structure shielding it from the heat. A few, citing old NASA comet models, predicted total disintegration, a silent evaporation that would leave nothing but a faint dust cloud when it reappeared. But the professionals weren't idle. Even in silence, they prepared. The Atacama Large Millimeter Array, ALMA, scheduled an emergency observation block for November 18th, anticipating the first post-conjunction window. The infrared telescope facility recalibrated its sensors for rapid follow-up spectroscopy. And the Deep Space Network, typically reserved for communications with planetary probes, quietly allocated a listening slot, a narrow beam scanning the empty coordinates where Atlas would return. Unofficially, some believed the object could emit again, not optically, but electromagnetically. If the radio pulse detected by LOFAR and Blue Origin was part of a recurring phenomenon, another burst might accompany its perihelion passage. The 155 MHz frequency band was kept open by several observatories just in case. But there was one detail everyone noticed: the alignment. When Atlas disappeared behind the Sun, its line of sight intersected active region AR3419, a patch of the solar surface dense with magnetic loops. That means any gas or dust ejected by the comet would have entered the strongest part of the Sun's magnetosphere, a region capable of trapping charged particles and amplifying their signatures. If Atlas was venting metallic plasma, that interaction could produce a temporary halo of emission, invisible to us but measurable by space-based detectors. So while the optical telescopes waited, the solar instruments listened. The Parker Solar Probe, looping close to the Sun on its 20th perihelion, extended its magnetometer range just slightly, enough to catch anomalies outside the usual solar wind profile. Between October 31st and November 2nd, it did record something, a faint rhythmic fluctuation in particle density, repeating every 19 hours, the same as Atlas's rotation period. The team hesitated to connect it directly, but the signature was uncanny, like a heartbeat echoing through the Sun's corona. Still, without direct visual data, no conclusions could be drawn. The official explanation labelled the signal as periodic solar wave interference. But several researchers who had been tracking Atlas before conjunction noted the coincidence quietly among themselves. Whatever is happening, one said, it hasn't stopped. The silence that followed wasn't empty. It was charged, awaiting silence, filled with the tension of knowing something extraordinary might be happening just out of sight. Every model pointed to the same time frame. By November 17th, Atlas should begin to emerge from behind the Sun, faint at first, then brightening again as it recedes. If it survived intact, its chemistry would shift once more, cooler, slower, revealing what months of heating had changed inside. If it didn't, there would be only residue, and so the world waits, instruments idle, data channels open, eyes fixed on the coordinates where a green traveller will soon reappear, older, maybe quieter, but still carrying secrets from another star, because when the signal resumes, every telescope on Earth will be listening. Observatories worldwide coordinate to resume tracking once it re-emerges, aiming to catch the reactivation. November 17th, 2025. Just before dawn in Chile's Atacama Desert, a technician inside the ALMA control room received a faint signal alert, a subtle rise in thermal noise exactly where the simulation said it would appear. At first it looked like a routine false positive, but when they cross-checked against the latest heliocentric coordinates, the realization hit. 3, I-Atlas was back. The object had survived the solar crossing. Within hours, telescopes across the planet came online. The European Southern Observatory reactivated its VLT spectrographs. The infrared telescope facility in Hawaii swung into position, followed by the Lowell Discovery Telescope in Arizona. Even the James Webb Space Telescope, now clear of the Sun's blinding proximity, began allocating emergency observation slots under its Target of Opportunity protocol. The coordination was unlike anything since Oumuamua. The International Astronomical Union opened a dedicated monitoring channel, where institutions shared raw data in real time, a digital nerve centre stretching from La Palma to Mauna Kea, from Canberra to Pretoria. For once, global astronomy moved like a single organism, and then came the confirmation. At 0642 UTC, a narrowband spectral line appeared on multiple instruments, a clean CN emission at 388 nanometers, faint but unmistakable. Cyanogen again, glowing through the dark like the pulse of a survivor. The comet was fainter than before, its coma more compact, its tail shortened. But its chemistry was alive. In fact, early photometry hinted that Atlas might be entering a second phase of activity, one even more curious than the first. Its colour index had shifted, less green, more turquoise, with flashes of deep violet under certain filters. That colour change suggests the release of new compounds, possibly nickel oxides formed during its passage behind the Sun. The object's rotation period, measured from light curve oscillations, remained stable at 19.04 hours. That stability shocked scientists. If Atlas had fragmented, its rotation would have changed. Instead, the timing held, implying the nucleus endured intact. Its layered structure, whatever its composition, had survived solar heating near 2.5 astronomical units, temperatures high enough to shatter most comets. The silence of October was over. Now the data stream flowed again, and what it showed was stranger than anyone expected. Infrared measurements revealed an unexpected rise in surface emissivity, the ability of a material to radiate heat. Atlas was cooling faster than models allowed, as though its skin had become reflective or metallic. One theory held that sublimation had deposited a thin nickel film across parts of the nucleus, turning it into a natural mirror that shed heat efficiently. Another suggested electrostatic dust alignment, forming reflective microcrystals along magnetic field lines. Whatever the cause, it gave the comet an unusual sheen. Long exposure images from the Las Cumbres network captured a faint halo, shimmering like oil on water, a texture so smooth that astronomers nicknamed it the mirror phase. Then came the first radio ping. On November 20th, LOFAR resumed monitoring the 155 MHz band, the same frequency that had once lit up with the mysterious odd radio circle. At 4:13 UTC, an identical spike appeared, weaker but perfectly clean, lasting 1.1 seconds. It repeated twice more over the next 48 hours. This time, no one could call it coincidence. The signal correlated exactly with Atlas's rotation, as if every full spin produced a momentary pulse, a flash of interaction between its venting gases and the solar wind. ESE's solar orbiter, positioned closer to the Sun, recorded synchronized microfluctuations in plasma density, confirming that the pulses weren't instrumental artifacts but real space events. The working model now reads like science fiction. Each time Atlas turns, a jet of charged CO2 and nickel dust aligns, with the interplanetary magnetic field, generating a low-frequency burst as particles accelerate along field lines. It's a natural plasma antenna, a comet that literally broadcasts its own chemistry. Across observatories, researchers began speaking in whispers again. "It's alive," one engineer muttered in disbelief as the radio pattern stabilized. "It's breathing again." But this time the tone was different. There was no panic, no rush to suppress discussion. The coordination was transparent. Data was shared openly, peer-reviewed in real time, streamed across continents. For the first time since the discovery, the study of 3I Atlas felt like a collective endeavour rather than a competition. Every new observation pointed toward one conclusion: 3I Atlas is stable. Its internal mechanisms, just whether purely physical or chemically self-regulating, survived the Sun and resumed operation with mechanical precision. It had weathered the closest thing to death a comet can face and come back organised, methodical, unchanged. And now, with the global watch renewed, the question shifts from survival to meaning. What does it represent? This 10 billion-year-old fragment that refuses to conform? What does its endurance tell us about the diversity of worlds scattered through the galaxy? Because even as the world's instruments refocus, there's a growing sense that we're witnessing something bigger than a comet's return. We're watching the cosmos itself demonstrate its patience, a process billions of years old, continuing flawlessly after a brief eclipse. The reactivation confirms one thing above all: 3I Atlas isn't finished. Its final secrets are still locked inside, waiting for the next threshold, the next pulse, the next light. How this one object could redefine our understanding of planetary system chemistry and interstellar diversity. Now that 3I Atlas has re-emerged and stabilized, the science community is finally catching its breath. The initial wave of disbelief has given way to cautious clarity. It's not an alien artifact, not a coded message, but it is something equally profound: direct evidence that the chemistry of worlds beyond our Sun can be radically, beautifully different. In the simplest terms, 3I Atlas is rewriting what we thought normal meant. Its extreme CO2 dominance, nickel without iron, delayed cyanogen, and threshold-based activation are not random quirks. They are a coherent expression of a foreign planetary recipe, a blueprint from a galactic epoch where the elements themselves follow different rules. Every solar system is a chemical fingerprint, shaped by its parent star. Our comets reflect the Sun's chemistry: oxygen-rich, water-heavy, built in a region where iron and silicates ruled. But 3I Atlas was born elsewhere, in the Milky Way's thick disk, amid stars starved of metals, surrounded by carbon-rich, oxygen-poor dust. Its existence confirms that entire classes of planetary systems may operate on completely alien chemistry, where CO2 replaces water, where metals cool instead of oxidize, where volatile gases freeze into layers we've never seen before. For planetary science, this is seismic. It means our search for habitable worlds, for Earth-like planets, has been far too narrow. Life, if it exists elsewhere, may arise under chemical conditions so foreign that our definitions of organic, liquid, or even stable no longer apply. Atlas's composition suggests that planets from such systems could host atmospheres of carbon dioxide and nitriles, oceans of condensed carbon compounds, and metallic crusts that regulate heat like mirrors. It also reframes what interstellar comets truly are. Until now, we treated them as random debris, travellers passing through. But 3I Atlas behaves more like a message in a bottle, carrying the unaltered record of its home system's physics. Its layered ices are geological time capsules, preserving the gradients of temperature and radiation that shaped them billions of years ago. In a single nucleus less than 10 kilometers wide, we're holding a cross-section of the early Milky Way. What makes Atlas exceptional is its continuity. Even after billions of years drifting through interstellar radiation and cosmic dust, it hasn't broken apart. Its crust is denser than expected, its internal chemistry self-regulating. That resilience may be why it survived the Sun's heat intact. It's a system designed, by nature, not intent, to endure. A structure so ancient it almost seems alive simply because it refuses to decay. And that's where the philosophical weight of this discovery settles in. Atlas isn't just a comet. It's a demonstration that the universe engineers stability from chaos. It doesn't need intention to create design. Over enough time, randomness can sculpt systems that mimic purpose, precision, and rhythm. Even the so-called breathing cycles, those 19-hour emissions, those perfect activation thresholds, may be nature's own form of memory, patterns locked in ice by eons of repetition. In that sense, Atlas behaves like a frozen echo of its parent star's history. Every pulse we record could be the rhythm of an ancient orbit, replayed across the gulf of interstellar space. There's still much to learn. Over the next months, the James Webb Space Telescope will continue deep spectroscopy of Atlas's tail, searching for isotopic signatures that could link it to specific stellar populations. The Parker Solar Probe and Solar Orbiter remain tuned to detect any recurring low-frequency bursts, and by early December, Earth-based telescopes will measure whether the comet's rotation is changing, a key indicator of internal pressure and structure. But already, the data is forcing new questions. If interstellar bodies like Atlas are this diverse, how many others have passed us unnoticed? Dark, inactive, indistinguishable from asteroids. Could our own Oort cloud contain relics of similar origin, captured long ago? And more provocatively, what if the chemistry we see in Atlas isn't the exception but the norm, and our water-rich world is the anomaly? The implications extend beyond science. For the first time, we're seeing physical proof that the universe doesn't just make variety, it preserves it perfectly for eons. Atlas is the cosmic embodiment of endurance, of patience, of balance without control. When we look at it, we're looking at an answer to an old question. How much of creation is accident and how much is structure? 3i Atlas blurs that line, its chaos refined into rhythm, randomness hardened into design. It tells us that the universe doesn't always need life to act alive. Sometimes it builds systems so intricate, so resilient, that they simulate intention and endure long after their origins are forgotten. When historians of science look back on this moment, they may not remember the data tables or the press releases. They'll remember that, for the first time, we saw a piece of another galaxy's chemistry drifting past our sun, and we recognized it for what it was: a survivor, a messenger, a mirror of what the cosmos once was and what it still may be. A calm reflection on what 3i Atlas has already revealed, and the uneasy realization that its strangest phase may begin when we can no longer see it. It's late November now. The object that arrived from another star, the one we've tracked for months through chemistry, silence and light, is fading. Each night it sinks lower toward the horizon, its colour dimming, its pulse slowing. Soon it will be gone, not destroyed, but too far, too faint, swallowed again by the dark between stars. But before it vanishes, we're left with something more enduring than the comet itself: understanding. 3. Atlas has shown us that the universe doesn't obey our sense of simplicity. It breathes complexity into ice, precision into randomness, order into dust. It taught us that even in deep time, billions of years before our sun existed, the cosmos was already building structure, testing chemistry, layering patience into matter. When we found Atlas, we looked for an explanation. What we discovered instead was a mirror. It reflected not our technology or our science, but our curiosity. That human impulse to read patterns into the unknown, to listen for rhythm in the void, and perhaps that's what it truly represents. Not an alien signal, but a cosmic invitation to think differently. To realize that the story of the universe isn't just ours. Somewhere, long before Earth cooled, this fragment froze in the light of another sun. It wandered for billions of years through the empty dark, carrying the memory of its origin in every atom. Now it's leaving, unchanged by our brief attention, indifferent to our fascination. And still, we can't help but feel it noticed us. Not in any conscious way, but in the simple fact that its presence demanded we pay attention. When future astronomers replay these months, the CO2 storms, the radio pulses, the synchronized heartbeat, they'll see data points, not wonder. But for those who watched it live, this was something more than science. It was a glimpse of how alive the inanimate can seem when it's arranged by time, gravity, and chance into something that moves with purpose. 3. Atlas reminded us that the cosmos is still writing, that every frozen traveller is a fragment of its handwriting, still legible if we learn to read it. Soon it will slip back into interstellar space invisible again, maybe for 1,000,000 years, maybe forever, yet its echo will remain in the data, in the images, in the quiet realization that we've touched, however briefly, a memory older than the sun. And when it disappears, the sky will look the same as it always has. But those who saw it will know better. Somewhere out there, beyond the warmth of our system, something continues to move, layered, breathing, patient, carrying secrets that no star has yet burned bright enough to reveal. And so the record ends, not with discovery, but with distance. The green traveller fades, leaving us with a single thought that humbles and unsettles in equal measure. The universe doesn't need witnesses to make wonders, it makes them anyway, and lets them drift.